Hello everyone. Today I'm going to give a tutorial on PRISMS-TwinID, which is a MATLAB script to perform deformation twinning and twin variance identification in magnesium from in-situ EBSD data. So first, I will talk about some background information and then give an overview of the data processing procedure and algorithm. And then we're going to look at an example of how to run the codes using data from a real sample. First, for the background, experimentally, we perform in-situ mechanical testing inside a scanning electron microscope using a miniature loading stage, and we use a strain gauge attached to the side of the sample surface for real-time monitoring of the approximate global strain values. So this plot shows the relationship between stress and strain. And for the experiments that I performed, typically there are 2 load cycles and 14 load steps. These red dots indicate the strain levels or load steps at which we pass the test for EBSD characterization. For the EBSD, we always try to find a easily recognizable feature, such as a green boundary retrieval point or a particle on the sample surface, and we try to keep it in the center of the field of view for all these EBSD scans. So every time we are measuring approximately the same area of interest. And then the EBSD data of all these load steps are considered together for twinning identification. We are interested in twinning because twinning in magnesium it is an important deformation mechanism in magnesium, and the most common type of twinning in magnesium is this extension twinning. It has 6 variants, and we have assigned a specific number or ID to each of these variants. And in this MATLAB code, we only consider this type of twinning. Note that the definition of twin variant is dependent on the Euler angle that describes the crystal orientation. For example, for physically the same crystal orientation, if we use a different Euler angle to describe it, such that the A1, A2, and A3 axes have a relative rotation about the C-axis, we can see that although it's physically the same twin system, the twin variant number will change. That's the reason we need to consider information from all those steps. There are other reasons that we need to do this twinning identification. One is that note that the commercial OIM analysis software, it can provide some parent twin or maps, but there's no differentiation between the twin variants. Also, the parent orientation determination is dependent on the majority rule. For example, we compare the parent twin maps generated by OIM analysis for a few load steps. Comparing to the undeformed load step, we can see that if it is heavily deformed in this grain, if the twin area accounts for a majority of this parent grain area, it can be incorrectly identified as the parent orientation. Therefore, we need to consider information from all load steps. Now let's look at the data processing procedure. So the first step is to perform some data cleanup using OIM analysis, such as neighbor orientation correlation or grain dilation. And then we need to export these grain files. Due to the existence of twinning, there can be 2 types of grain grouping algorithm. The first is to ignore the twin boundaries so that the untwinned matrices and the twin area are considered as a single grain. And we call this type of grain the parent grain, and this data, the parent grain data. The other is to treat the twin boundaries as regular green boundaries so that the untwinned matrices and twin areas are considered as individual greens, and we call these the child greens, and this data the child green data, or simply green data. And we need to export data using both of these two green grouping algorithms. For example, this is our working directory. There are 14 load steps. This is what we have. So 14 load steps, and each load step we have 4 text files. So green file type 1, green file type 2, these are the child green files. And we have parent green file type 1 and type 2. So these are what we have for data. Okay, back to our presentation. So the next step is to perform spatial correlation of the EBSD data at different load steps that can help us track the same green in all these load steps. For example, if we plot the EBSD data or the EBSD green file of different load steps according to their spatial coordinates, we can see that typically they do not overlap well. That's partially because of sample deformation and partially because these EBSD scans were typically not performed to exactly the same area. So to perform the alignment, we can select some easily recognizable greens, although it's optional but strongly recommended, and use these the center of these greens as control points to perform a 2D affine transformation. And this affine transformation can also be used to estimate the approximate global strain of the area of interest. And we can see that after this alignment, the green boundaries overlap has a significant improvement. Therefore, we can easily recognize the same parent green in different load steps based on their spatial overlap. Observation of this type of map helps us to recognize another problem. That is, these greens, some greens are not defined in a consistent manner. For example, this green boundary, it only shows on map as one load step, but not on the other. So we need to select these type of greens either to merge two greens into one green, which is relatively simple, or sometimes, most of the time, we need to select this green at load step 2 and manually divide it into two greens. And in this next slide is an example. So here we can see that at load step 0, the undeformed load step, there are two greens in the center of this area of interest. At a deformed load step, this whole area is considered as one green. So we want to add a green boundary here. So we first check the child greens. If there are child green boundaries that can be used to divide this parent green, we draw a mask and use the child green boundary to divide it. If there are not child greens boundaries usable, we plot map that shows the maximum misorientation of each pixel with respect to its 4 neighboring pixels. And then we draw a mask to cover an area, and we select the points under the mask with this max misorientation larger than a threshold value, say 5 degrees, and use it as an additional boundary and add it to the original green boundary, and use these green boundaries to divide this parent green. So after this step, this processing. Then finally, we go to the identification. For each undeformed parent grain, we can find a deformed parent grain, and therefore all its child grains. The child grains, such as child grain 182, 178, that has similar orientation to the undeformed parent grain, um, they are considered to represent the deformed parent grain orientation. So their average orientation is calculated to represent the deformed parent orientation. The remaining child grains, such as in this case grain 177, are determined for whether being a twin, and if it is a twin, which twin variant it is. To perform the identification, we calculate the orientation of each possible variant for the deformed parent orientation, and we compare the misorientation with the child grain of interest. And if a misorientation is small enough and smaller than all other possible variants, then we say this child grain is a twin of this twin variant. This was performed on the grain level, so this whole child grain 177. We can also perform this similar analysis to each pixel in this child grain. And because of the variance of pixel orientation, the results can be slightly different. So we end up with getting this type of identification map. So on these maps, each twin variant is labeled using a different color. So overall, this is the identification algorithm. And in the next section, we are going to look at the example of how to run this MATLAB script using data from a real sample. The MATLAB script can be downloaded from this GitHub address. After downloading, this is what you have in your folder. This twin identification from EBSD, this code is the main program that we need to run. There are custom functions stored in this folder. There are setting files. These are the files you need to modify for each of your sample. This script includes some interactive selection of grains. So the suggestion is to run this code section by section using this run section. So basically, we run this code interactively. The first section is to select the setting file. For example, if we run this section, this mag for aluminum U2 is the sample that we want to process as example. So this is the file that we just selected. There are variables in this file, and this file is in .m format, so it is both human readable and also MATLAB can run it as a script. After running, these variables can be directly imported. So the meaning of these variables, so this is the working directory, the directory that contains our data. So this one, this is a folder that the script just created to store data for our analysis. This is the sample name. This is the maximum load step that we have in our test. So we have 14 load steps from 0 to 13. This is the minimum grain size that we have in the EBSD cleanup for the grain dilation. So it means that any grain smaller than 16 data points were merged into the larger grains. This is an example of the format of the grain files. So for these grain files. These two variables, they help to plot the results. So it indicates like which load step is the end of first load cycle, end of second load cycle, things like that. And this is like the strain gauge reading for each load cycles, load steps. The screen pair, these are the grains that we have manually selected at each load step, and we use these grain centers as control points to align the EBSD data. So we have 14 rows, and each row we have the ID of 4 grains that we have selected as control grains. So if you have a new sample at the beginning, this variable is empty, and you need to interactively select some grains and modify this variable. This ID list, it contains for each load step the grains that the ID of the grains that you have selected, and you want to divide the grain into 2 grains. And for example, if you want to divide it into 3 grains, you can you need to so type the grain ID here twice. So each time it only divide it into 1 more grain. And this ID merge list is, so for each row, it is in the format like you want to merge grain 84 into grain 85. And if you have another grain pair you want to merge, you input it in another row. So basically, that's all the variables we have in this setting file and their meaning. Now we go back to our main program and we run the next section. So this section, it basically reads the text grain files and extracts the variables and align the all angle of the crystal coordinate with the sample coordinate. And then it saves these variables in a .mat format that can be easily accessible by MATLAB. The alignment of the all angles is done in this function. So it processes both the pixel level all angles and grain level all angles. And these are the sequence of rotations you need to apply for the alignment. And this is dependent on your SEM setting. So these 3 angles are what we have for the SEM in our lab. And yeah, you can see these process will take a while, and let's wait for a while and then see the results. Okay, now section 1 is done. We can look at our folder. We can look at this analysis folder. So these are the files generated in this step. If we cd to this directory, we can see that these are the variables that are extracted, aligned, and saved in each of these grain files. So parent grain file and grain file. And now we can proceed to the next step, step 2. If we run this section, so it processes each load step and plots these grain ID maps and auto grain maps, where each grain has a unique color that is different from its neighboring grains. These maps are stored in this analysis folder, and overall, these maps, we can later look at these maps one by one and help us to determine which are the grains that we want to select as control grains for the alignment of EBSD data of different load steps. So these grain ID maps, this one and these ones, they are stored in two formats. One in .fig format that can be easily opened by MATLAB, and also you can use this tool to look at the green ID. These ones and these ones, basically they're the same map in different formats. These ones are the auto green map, and we can look at different load steps. For example, this green, we can see that the definition is not good. We want to like add a green boundary here. But for greens like this, the definition is very consistent in all these different load steps. So this is a green that is good to be selected as a control green to align the EBSD data of different load steps. If the greens are already selected, for example, we already have them in our setting file here, the green IDs will be labeled on this map. If you don't have it yet, these they are not labeled, but you can, after you have input and modified this variable, you can run that section again. So it will label these greens and help you to visualize what are the greens you have selected. Okay, so this section is done. We can proceed to the next section. This section will perform alignment of the EBSD data of different load steps. It can use the control greens that you have just selected. That is strongly recommended. If not, it can also do a guess, and at the end it will plot a green boundary map. You see, this is the aligned green boundary of all these 14 load steps using different colors. It can help you visualize the quality of the alignment. This seems good, so we can move on and do the next section. In this section, we're going to select the greens that we want to divide it into more greens. Previously, I have disabled this section. Let me enable it. And we can run this section. Yeah, so it labels the greens that we have already selected using these red colors. Basically, we are searching for greens that we have a green boundary that appears in the middle of the green, because these green boundaries are all the 14 load steps. The green boundaries from all load steps are plotted, and the greens are plotted using a unique color for each green. So if it is a green with a boundary in the middle, it means that so this is a single green, but in other load steps, it appears as two greens. So we can select this green and to divide it into two greens. So this is an interactive step. So we need to, for each load step, we need to observe the map and manually select these greens. For example, we have already selected these greens. If we want to select this one, we can just click it, double click it to confirm, and then we can select other greens and double click to confirm. After performing this selection, we can just close the map, and it will go to the next step. And in this command window, it shows us which are greens that we have already selected. You see, these are the previous greens. We have just added two greens. These based on this line, we can later go back and modify modify this variable in our setting file. So we can proceed for all these load steps one by one and select the greens that we want to divide into 2 greens. We have already selected all of them, so we're just closing all these windows one by one. Okay, now this section is done. Assume we have modified these greens. We can move on to the next section. The next section is similar, so the purpose is to select the greens that we want to merge. For example, if we want to merge this green with this one, we can first select this green, double click, it's labeled red, and then we can select this green, it's labeled white. So this is a pair. So we have completed the selection of a pair, and we can move on and select other pairs. Assume we have finished this selection, we can close this window and move on to the next step. And also this command window will display the pairs we have just selected. And based on this, we can later go back and modify this variable, so the ID merge list. And because we have previously finished this selection, we can just close all these windows. Okay, so this selection is done. And then we can go to the next section, which is for each of these, for each load step, for each of the selected greens that we want to divide them into 2 greens, it will let us manually draw the masks to select the boundaries that we want to use to divide the greens. Let's run this section. It will process each load step and each of the greens that we have selected for dividing. So for this green, we want to add a green boundary here. This is a child green map where each child green is labeled by a different color. We see that this is the same parent green, also the same child green. There is not a green boundary here that we can use. So we can close this window, and it will give us another option, which is to use the max misorientation. We can see that this here seems to be a green boundary that we can add and use it to divide this green into 2. This currently it plots the threshold value is 5 degrees. So it plots the pixels with max misorientation larger than 5 degrees. So we can draw a mask to cover this area and select this part of pixels. Currently, it is not a continuous boundary, but the code will iteratively reduce the threshold each time by 0.5 degrees. So ultimately, it should find a continuous boundary that can be added to this original boundary and use this boundary map to divide this green into 2 greens. So after selection, this mask, we can double click to confirm. If it's okay, it will proceed to the next green. Similarly, the child green map is not usable. We close this window go to the next option to use the max misorientation map. This time at the 5-degree threshold, this is already a continuous boundary that can be added. So it should work. And now go to the next green. This is the green where the child green map is usable. For example, this parent green where the boundary is colored white, there is a child green boundary. So you see these two different colors indicates two child greens. We can use this child green boundary to divide this parent green into two greens. So we can directly draw the mask on the parent green, on the child green map, and double click to confirm. So the child green boundary can be used to divide the parent green. This is a similar situation. We draw a mask here. Now we just proceed for each green. You see, we have previously just finished the load step 0. Now we're processing load step 1. So we have finished all the 4 greens that we have selected for load step 0. So this process will take a while, so we can just proceed. I will do this process, and later we can come back and see what we have and go to the next steps. Now we have finished modifying the parent greens. We can continue and then modify the child greens. Modification of the child green is a relatively fast process. Okay, so the child greens have been modified, and no more plots will be created, but we can see that we have folders for each steps of this code. Data after each step will be stored in their folder as a backup, but the updated files will be kept in the main folder. After modifying these files, in the next section, we will perform the fine transformation and align the EBSD maps again, because the files, the green definition have been modified, and it will plot maps which can help illustrating the quality of this process. And you see, it will create this type of map. It shows the undeformed green ID map aligned and transformed to a deformed load step, and it shows the linked green ID to the deformed load step. Briefly, if it shows a color here, it means it can find a match. Otherwise, the green will be plotted with a white or transparent color. And after this alignment, we can go to the next step. It try to modify the green IDs so that for the same parent green, at all load steps, it will be assigned with the same green ID, so that in the following steps, by simply checking the green ID, we can find the same parent green in all these load steps. And it will also create some illustration here, these maps. So it gives a summary. It plots the green map at each load step, and it plots the last digit of the modified parent green ID. So briefly, it means that if in all these load steps, a parent green has the same color, very likely the green is matched very well in these load steps. For example, this green, you see the color is consistent. While for some edge greens like this, the color changes. It means that a match is not able to be found. So, but we can see that that basically occurs for these edge greens. There's no good way to well correlate them and process them. For most of these areas in the center, we see the match is very well. And this part is done. These does similar things like copying the backup files from the folder after this section to the main folder. And so the previous sections are the pre-processing, and now we go to this part 5 is to find out the variance. So it will process each load step using the algorithm we described and find variance for each twin grain and for each twin pixels. Okay, now we have finished this section of twinning identification. It creates these identification results. These ones are for the green level. These ones are on the pixel level, where identification was performed to each pixel. And we can look at the maps of each individual load steps to look at the results. Here is the identification results. I have in another folder of the original EBSD maps. For example, we can compare. This is the EBSD data at load step 1. This is our identification results. We can see that all these twin areas are correctly identified. So after this step, the following steps will be to plot some summary. For example, this step is to summarize the twin percent at each load step, and this one is to calculate the EBSD estimated strain from the affine transformation, and then plot. So the plots are saved here. It plots the twin area percent in our sample versus the EBSD estimated strain, and this plot is for the strain gauge strain, and the strain gauge reading, EBSD strain, and twin percent, and the twin area standard deviation at different load steps are summarized in a table. It is also saved as an image, so the table is here, and the image is this one. Yeah. So basically, this is overall how the code runs on a data from real sample. I hope this will help, and please let me know if you have any further questions. Thank you.